That's not our lives, so hey guys, what's going on? We are back at the Physics Monastery after another critical vehicle breakdown and several plane flights later. We're back in Utah. So, how are we all doing here? Now, I did a little ad hoc broadcast from several days back. When was that? Oh, I think that was Sunday. Let's double check the records. Why? Because we can. And there is no actual scheduled topic, just sharing some stuff and things out there into the greater internet ether. As we let different folks roll on in from across the web, from the YouTube, the X Twitter, the blue skies, this and that. I remind me, I should probably actually share that to one of those other places. Let's do that right now. All right. Where are we? Okay, we can click that thing there. There we go. All right. Those folks are rolling in, and those who may join us temporarily in the future are welcome. And I'm just going to do a little catch. Yes, I realize there's a bigger whiteboard behind me with a whole lot of different stuff and things on it. And we can go through some of that. Do this first. Boom, boom, bada boom, and bada bing. All right. So you go there. Just keep swimming. Just keep swimming. All right. So let's do this. Let's go back to our other thing from the other day. Why? Because we can. All right. Let's your screen. Boom. All right. Where are we at? Yeah. Here's where we are. Ooh, the nothingness. All right. And then we're back over here. What was this from the other day? New CERN CMS results suggest the Higgs boson mass may be tuned to H bar. Yeah, well, that is my conjecture, but we actually have the paper and stuff and everything over there. So we went through that, and hold on, what do we have? Let's go over. A lot of people may kind of glance over. Hold on. Okay. So let's just reframe this for a second, and let's go past me. Say some word here right now. Okay. Well, this was posted last evening, uh, or yesterday afternoon, technically. And as we can see, it's from the CMS publications here. I know, such an engaging name. And this is something that I feel a lot of people may kind of glance over and they're like, okay, whatever. So basically, they've done further analysis of the data that they've collected over the number of past runs at the Large Hadron Collider, in particular, the CMS experiment itself. Okay. And basically, they're measuring the mass along with the width of the Higgs boson. Today, we're going to be focusing specifically on the mass of the Higgs boson. Why? Well, because they actually had some results that got me pretty excited. So we'll get into it here. As we can see, they have the combined measurements here. You see all this stuff here. Here's the thing. I'm not a trained particle physicist. I don't know what all this stuff means, full disclosure. But what I do notice is some of these things where you start going through, and hold on, I'll get to it in a second. And then they actually have the prediction. Welcome, Sky of Mine. Text. So okay, I recognize the symbol, not the name. The current estimated mass of the Higgs boson has been revised, and according to the CMS collaboration now, the estimated mass of the Higgs boson, aka the God particle, is 125.38 giga-electron volts, effectively divided by like c squared, because if you're going to get a mass, but that's its mass energy equivalence. Okay. I know, I'm just showing a tweet here. Who cares? Okay, let's actually get into something a little bit deeper here. So let's. Okay, so that was from the other day. So let's go in. Why am I saying this? Why was I even excited at all? That's who knows. All right, let's delve into a video we posted a wee bit earlier, and this might explain why. Because here's the thing. I ain't no genius or something. If anything, I don't know any better. In this video, Professor Carroll is going to highlight why I'm not a good physicist. So we'll bring this up right now. Screen, boom, boom. All right. So this guy right here, as we can see, I titled this video, Good Physicists May Miss This. Why? Because as the quote says, every good physicist sets h bar equal to 1. Why? Because you don't have to remember all the dang numbers. It makes things easier. However, if we set it using natural units, perhaps we may miss something deeply hidden. Go to the video.
But to fit the data that he knew about, the quantization condition, the chunkiness of which these electrons had to participate, was also characterized by the same number as what Planck came up with, the same constant of nature, Planck's constant. By the way, you might want to know, what is the number, Planck's constant? It's some number of joules, seconds, whatever it is. I have no idea what it is, because every good physicist sets h bar equal to 1, just like we set the speed of light equal to 1, and then we get on with our lives, because no one remembers how many joules or whatever per second h bar is.
What's known as the hierarchy problem. That's the question of why the mass of the Higgs boson is so much smaller than the Planck mass.
Effectively, we think that the Higgs boson should have a mass 10 to the 18 times bigger than it does. And so this is the hierarchy problem, and the hierarchy is just the mass scale that we expect and the mass scale that we see everything else sitting at. And the fact that there's 10 to the 18 differences, I mean, really 10 to the 32, because it's squared, and that's the real first principles number. The fact that something can be off by 32 orders of magnitude from our theoretical predictions, where did that come from, right?
Good question.
But to fit the data that he knew about, the quantization condition, the chunkiness of which these electrons had to participate, was also characterized by the same number as what Planck came up with, the same constant of nature, Planck's constant. By the way, you might want to know, what is the number, Planck's constant? It's some number of joules, seconds, whatever it is. I have no idea what it is, because every good physicist sets h bar equal to 1, just like we set the speed of light equal to 1, and then we get on with our lives, because no one remembers how many joules or whatever per second h bar is.
Okay. So the reason we showed that, let's go back to the last
h bar is.
Okay, hold on.
No one remembers.
Okay. So the whole point, hey, K-Shell, good to see you. Yes, we're just going back over a wee bit of history. We don't have anything specific scheduled. I'm just kind of rehashing over the past few days, over the travels and another catastrophic vehicle failure, the standard stuff that happens. But the whole point is ultimately one of CERN's collaborations, the CMS collaboration, who coincidentally, congratulations to them for winning the Breakthrough Prize. I think it's well deserved. I am also very biased on this because I also really like their results. Why do I say this? Because long story short is this paper that came out, I think it was actually accepted on January, towards the end of January. I didn't notice it until this weekend, but basically they have an expectation for the Higgs boson mass of 125.38 giga-electron volts, the mass energy equivalent of the Higgs boson. Why is this interesting at all? Because we put forth a little bit of a conjecture that perhaps the mass of the Higgs boson is tuned to the magnitude of h bar. Why? That's a great question. I can't say that I know. I was just kind of following a hunch, and from not being a good physicist and not setting h bar to 1, I recognize these first 3 digits and corresponding exponential power, which happens to match the magnitude of h bar. So Wolfram Alpha rounds there. So as we can see, our first 3 digits, if we take the mass of the Higgs boson, we divide it by the Planck mass, it gives us the dimensionless number. Okay. Now that straight number, I couldn't make sense of. So I had to square it. When I squared it, then I was able to start to make a little bit of sense of it, because I recognized these first 3 significant digits and that corresponding exponential power. When we look over to what h bar is, blah, 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 1.05 times 10 to the minus 34 joule seconds. That seems interesting. Again, just a coincidence because it's like, well, why am I squaring that? Where Dr. Cesarati comes in. As we can see, this is the links and everything are in the doobly-doo. But if we go to this, so ultimately, first it was Dr. Hassenfeld that's just described like the hierarchy. Let's just go back to it. The hierarchy problem. What is the hierarchy problem?
What's known as the hierarchy problem. That's the question of why the mass of the Higgs boson is so much smaller than the Planck mass.
Okay. So if that's the problem, here's the general result right here. Now, I can't make sense of that. That's the thing. That's legitimately just out of curiosity. I squared it, and then I noticed something. But what's the justification? You need something better than that means. Okay. That's why it didn't hurt to listen to Professor Sean Carroll's Mindscape podcast. And then he had Dr. Cesarati on. So let's take it away and explain more precisely what the first principle of the hierarchy problem should be.
Effectively, we think that the Higgs boson should have a mass 10 to the 18 times bigger than it does.
To be fair, he said 10 to the 18. If you do the inverse, it's still about 10 to the minus or 10 to the 17 there. It's like 10 to 9.8 times 10 to the 16. Listen, it is hard to remember. That's one of the reasons why everybody sets it to, or at least good physicists set it to 1. Because if it was 10 to the 18, if you squared that, it would be 10 to the 36. And then she does actually kind of correct it a little bit and say it's 10 to the 32, which is, again, you're within the magnitude range. I understand what she's saying, but just for clarification, it should actually be about 10 to the 17. I could be wrong, but I think that's what it is.
And so this is the hierarchy problem, and the hierarchy is just the mass scale that we expect and the mass scale that we see everything else sitting at. And the fact that there's 10 to the 18 differences, I mean, really 10 to the 32 because it's squared and that's the real first principles number. The fact that something could be off by 32 orders of magnitude from our theoretical predictions, where did that come from?
That's a fantastic question. Where did that come from? Now, again, I'm not saying that this is the answer. I'm just saying that if we were to postulate that, I don't know, perhaps maybe the sheer fact that we see a little coinky dink here, it happens to be the first couple of digits, correct corresponding power, the first couple of digits in corresponding power. Maybe there's some there, so to speak. Hey, Carly, welcome. Good to see you. What was that? To be fair, Carly, I think the original hierarchy problem was why was the mass of the electron so small? And apparently that's been figured out now. I think it actually has to do with the Higgs because then the lepton can get its 10 to like 10 to the minus 31 kilograms, something like that, and the proton neutron about 10 to the minus 27. Again, the only reason that I know that is because if you're actually searching for a potential piece of a puzzle, at least according to Thad's method, you spend a lot of time looking at a lot of digits. Don't remember all the digits, but I'm pretty good at remembering the first couple and the approximate magnitude. Because if we go further, we go. Okay, so the whole, I had to redo Professor Carroll's thing because just because this is the data I have available at the time. He's actually talking about, the Cody equation. Yeah, the Cody equation is basically, what was it? The hierarchy of like the quark masses, and as well as, the electron, the muon, and the tau. Basically, they both seem to follow the Cody equation. Let's actually bring that up real quick. That's actually kind of important, and that's actually a video that got a lot of attention from Thad because it's set equal to literally 2/3, or it's within the error of 2/3. Let's go to the Cody form. Here we go. Oh, it actually helps if I share the correct screen. Here we go. Share that. All right. So the Cody formula. Okay, so basically, if you take mass of the electron plus the mass of the muon plus the mass of the tau, and then you sum the square roots, you square it, it's basically equal to 2/3. So, okay, so this does appear to only be for the electron, muon, and tau, at least those leptons. So speculation may suggest maybe the neutrinos follow a similar pattern. Again, there's a lot of different takes on that. Could be just that seesaw mechanism. Maybe one of them is massless. I don't know. I'm a simple type of guy. I'm like, oh, if this holds, might we be able to explain something similar? Again, I don't know, but it is an interesting thing to take a look at. So let's go back to our what good physicists may miss. Here, all right. So basically, in this next part, Professor Carroll is going to be talking about, I believe it was, he's actually talking about Bohr coming up with the Bohr radius and stuff, and having to utilize H bar basically as like the energy levels. Or that's my best knowledge. Let's kind of dig it away.
Right.
But to fit the data that he knew about, the quantization condition that
actually, hold on. This
right.
But to fit the data.
Okay, so this actually was from. Okay, so it was in April. Okay, so this was literally within the past week or two. Cool.
That he knew about, the quantization condition, the chunkiness of which these electrons.
Okay. So that's my excitement right there. Why is that my excitement right there? Okay. So this is the CMS. Their previous stated value that they believed the Higgs to be was 125.35 GeV. Okay. It's gone up by what? Like 30 electron volts. Why is that important at all? Excuse me, 30 mega electron volts. Only off by a factor of like power 6. Magnitudes matter. Okay. We continue.
Had to participate was also characterized by the same number as what Planck came up with, the same constant.
The reason I'm just showing this is the Planck mass, because the question was originally the Planck mass. I'm just doing the Planck mass energy equivalent in giga-electron volts, just so we're comparing apples to apples. And it's a lot easier for me to remember the number in GeV versus just kilograms, because I don't know, personal bias. Colleagues say that the universe is hella nonlinear. Well, I think that's why we often use logs. And that's one of my two core postulates is math works and logs are useful. From that, I can at least try to tell a story. Now, I'm not saying it's the correct story, but we're following the evidence. We're going to see where it goes. So we have this number here, and then we're going to plug them into Wolfram alpha.
Also characterized by the same number as what Planck came up with, the same constant of nature.
Okay, so this is basically the current measurement. According to the CMS, I added a few more zeros, just so it would give me a little bit more information. But again, note that our data is cut off at the 5th significant digit. And even for this GeV, for the mass, for the Planck mass is energy equivalent, there is also error here. So just keep that in mind. So this ends up getting the first now 4 significant digits of the magnitude and corresponding power of H bar. Now, again, it's not in the correct units. H bar is in joule seconds. So I do this little trick, and again, maybe it's completely bunk. I've heard folks bring that up. That may be totally true. Or perhaps it's telling us something a little more. Do I know exactly what it is yet? No, but again, this is why we conjecture ahead. Here, let's cover our butts. Let's play our little conjecture thing. All right, where are we? Got to go past the trolling stuff. All right, Professor Wolfram.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Full disclosure, there's the MacBook Pro. We want to be as open and transparent as best we can. Okay. So let's continue with our little rehash here.
Planck's constant. By the way, you might want to know, what is the number Planck's constant? It's some number of joules, seconds, whatever it is. I have no idea what it is because every good physicist sets h bar equal to 1.
Okay. Now again, I'm not a good physicist. I did not set h bar equal to 1. However, perhaps not being a good physicist, or even like a real physicist, to be frankly honest, may have actually revealed something interesting. And again, only reason I looked at this is just because, well, Dad had been doing some work and it seemed to actually be making sense. So it's like, all right, let's apply this method and see where it goes. So let's go back for a second, take a look at this. All right, so what the heck is all this stuff here? Okay, so this is just our previous little thingy here. So when we get this is basically the CMS, current updated measurement. So this is, to our best knowledge, according to the CMS collaboration, they show the Higgs mass to be at the magnitude of 125.38 GeV. To be fair, I haven't gone through all the stuff yet and everything, and I need to, because we want to do our due diligence to factor in the error bars and everything. They just didn't have it immediately available that I saw as I was going through it. Okay, so we have our current CMS measurement, and this is just that number we had from CODATA for the Planck mass in giga electron volts. So AKA, we take the magnitude of the Planck mass and we multiply by c squared. Cool. Okay, so it gives us this number right here, which has the four significant digits and magnitude of h bar. And we go over here. What did we do? All we did was we took h bar, Planck's reduced constant, and we just divided the dimensions out. So the reference, excuse me. So h bar is expressed as a unit of action. Okay. So action is energy times time. Let me double check that because I just spoke words. I just want to make sure. Let's see, Planck energy. Planck. So I think that should give us. Yeah. Okay, that's correct. I had to double check myself there. Okay. So it's energy times time. Okay. It gives us that number there. Okay. So I just divided it out to make it dimensionless. Again, just a trick. Literally just a trick. Unless it may be more than a trick and maybe it's telling us something. I can't say that though. So basically, h bar is our elementary unit of action divided by the reference 1 of action, the joule second. Okay. As we can see, that gives us, it looks like 5 significant digits. It's kind of close because the next number is, if you rounded it up, it would be 5 significant digits, but we're going to hold it at 4 because that's just honestly what comes out. But again, this is something that if you're just utilizing setting h bar to 1, I don't think you would ever see this. I don't think, like, if you're a good physicist, you may not see this. Now, I'm sure there are plenty of good physicists that at least remember the first couple of significant digits of h bar. I'm pretty sure Stephen Wolfram would, because, well, Stephen Wolfram, and he still remembers all these particles from when he was a kid and like the approximate magnitudes. And I'm like, dang, he has a very high level of accuracy. I'm also just thinking that perhaps one of the reasons why he built Wolfram Alpha was it's kind of, I feel like, the computational database that he wanted to create as a kid. And he happened to create it when he was a big kid. So thank you, Professor Wolfram. Let's see. Makes a full Planck pi. Oh, that's interesting. See, that's because basically whenever you're putting in Planck's, the full Planck constant, I think that sets it equal to, let's actually go back. Let's just see. Because I think h bar either gives us the 2 pi Planck length, or one of them gives like 1 Planck length. Hold on, it's Planck's constant. God, what am I even divide? Oh, hold on. Planck constant divided by Planck mass times C. Okay, hold on. Let me stop that and read up the actual one. Okay, just so y'all can see what I'm doing. I'm not just a stark raving lunatic. Okay. So basically, if you want to find out, I think this is the equation to figure out like the wavelength of something. I think the constant wavelength of the Planck mass, because what we did was we took the Planck mass and then you have the Planck's constant as your base there, and then you divide it in and just multiply it by the speed of light. You get this. Okay, so that's interesting. Okay, yeah, so it gives us the 2 pi Planck length, and it gives us the first couple of digits of h bar there. So if we put in h bar, I think will go down. I think it will go down. Yeah, it should go down. Okay, so that gives us 1 Planck length. Okay. I'm saying that mostly for my own purpose because I knew it was one or the other. I just wanted to get it correct. Okay. We can go back to our video. Probably saying the lose is Planck divided by pi because photons are linear, not I don't know. When we say rotational, are we talking about, because technically photons, there's that complex rotation. So I think that's kind of where like the imaginary, the imaginary number comes from. Yes, the imaginary number I. When you first hear that, you're like, I have a letter. What are you talking about? But I don't know, some physicists and especially a lot of mathematicians, I don't know, they're very smart. All right, let's continue with a little statement and we'll wrap up about why I was getting giddy the other day. All right, back to our video. We'll continue. Okay, so we got about 4.5 significant digits of h bar, at least according to this measurement.
I have no idea what it is because every good physicist sets h bar equal to 1, just like we set the speed of.
Okay, so, and again, of course, if you're going to be going through a standard derivation, setting things equal to 1, and again, I do that with different Planck units and everything, it makes things so much easier. However, for setting equal to 1, perhaps we might miss some information rather than if we avoid utilizing the real numbers. And I don't know, maybe it's useful. Let's continue here. So, okay, so this whole thing is, if we were to assume there was some there, and again, could just be a straight coincidence, nothing to do with this. But basically, if we take, because we divided this on the other side before, so it's just the elementary unit of action, h bar, divided by the reference 1 of action, the joule second. So we're dividing it out to literally just make that dimensionless. We're going to get the units out, and then we're taking the magnitude of the Planck mass, energy equivalent in giga electron volts, which we just took right from CODATA. And now we're solving for X giga electron volts because we need to match the unit to cancel it out. And we're just literally solving for X.
Light equal to 1, and then we get on with our lives because no one remembers how many joules or whatever per second h bar is.
I don't remember how many joule seconds h bar is, but I at least recognize the first couple of digits and the corresponding magnitude. So basically, according to the paper, their estimate of the Higgs boson mass is 125.38 giga electron volts. When we solve for X, again, squared relationship there, so it could be positive, it could be negative. I'm including the negative just for full transparency. I think there's like some conjecture so that you can avoid negative math and stuff like that. Again, not a traditionally professionally trained physicist. I'm a dude on the internet. I'm gonna be very blessed that, like a lot of y'all, was very interested in this and somehow went from some internet troll interested in science to joining a physics monastery. You can't make this stuff up. But ultimately, that 125.38 giga electron volts is kind of close, in my opinion, to 125.376. And there's actually going to be an error of 2 on the end here. So it could go up It could go down a little bit because that's based upon the uncertainty and the Planck mass. Now, if we happen to put in that value for the Planck mass, it actually goes down to, I think, 125.37. I think it's like 5.7 or something like that. So pretty darn close. But at this point, it's within, this would be 100 mega electron volts. This would be, this would be, wait, is that only 10 electron volt? 10 mega electron volts. Is it down to kilo electron volts? I'm doing my math wrong, aren't I? Hold on. Yeah, 100 GeV, 10 G. Oh my God. Is it really within like 4 mega electron volts? Hold on. I'm gonna double check. Okay, let's do 120. Hold on, let me stop that screen. Present the other screen. Just I need y'all to keep me honest because I say a lot of words and a lot of the words that come out of my mouth are wrong. So GeV. Hey Tristan, good to see you, my friend. How we doing? These are fascinating times, man. These are fascinating times. I don't know where we're going. I don't know exactly where we've been, but I think we're in the era of we're going to see a lot of really cool stuff coming. All right, so let me just subtract that out. So 125.376 GeV. I'm going to have to put another zero. Just to get a little extra data. Okay, just because. Oh my God, it is within 4 mega electron volts. Don't that just beat all? And there is an error of 2, so it's outside of 1 cigarette, it's within 2 mega electron volts. Wow, that's pretty cool. I'm sorry. I got really excited when I saw the new CMS, and again, I only noticed it because of the dumpster fire that is Twitter, but very cool. Now again, I got to caveat this all. We're gonna need more higher precision measurements. Again, we had one measurement, an Atlas. It is still a little lower. I think the world average for Atlas is like it's about 125.11 GeV. I think technically the last one was actually 125.22, but the previous run was actually just under 125. But if we just kind of look at where the data is honing in, I got to redo some analysis and actually submit that paper now just because I'm sorry. Again, might just be a straight coincidence, but might it actually explain why the Higgs boson takes the mass that it does? Because I believe the argument would be, or this perhaps the postulate would be, the Higgs mass takes the mass that it does in order for the elementary unit of action to act. That's the most condensed sentence that I have for that. And I think if we think about it, because what was it, the weak force kind of breaks right around the magnitude of the Higgs boson. I think they have it estimated around the top quark mass or something, but basically it's like 10 to the 15 Kelvin. Extraordinarily hot, like 3 times, or I think 3 magnitudes above what the hottest things we have here on Earth are. So, because if we take our little prediction, let me just bring this back up. Share screen. Boom. Correct tab. All right, we are back here. If we take this, and what do we do? Boltzmann's constant, I believe. And this is literally the only reason I'm able to do this, just because I can literally type in words, and it feels like I'm just being like a wizard. It's like I'm literally just saying magic words, and it does. Okay, I did that completely wrong. All right, so obviously I need to divide by that. Here we go. Okay, so the unit conversion is, yeah, we get like 10 to the 15 Kelvin. What is this temperature? Okay, so if we go to, I'm gonna have to share the window. So we'll just go over here. So we have that guy. We'll just go over here and then electroweak force, electroweak interaction. Okay, so let's go down. Where will we have? Bunch of stuff. I'm not going to pretend like I know everything that's going on here. I do not. To be fair, I probably don't understand most of the things going on here. I'm sure a lot of other folks do, but okay. So let me just change so we can be big enough. All right. So we have, yeah. So the estimated, again, here we go. All right. After electroweak symmetry breaking. Okay. So in the history of the universe, this is believed to have happened shortly after the hot Big Bang, when the universe was at a temperature of 159.5 plus or minus 1/2 GeV, assuming the static and Bartle particle physics. Okay, so what is that? So let's make another Wolfram Alpha window, and we'll just do that. Just going to do the same thing. Copy, paste, and we're going to do that 159.5 GeV divided by Boltzmann's constant should give us a temperature. Okay, so again, it's a little bit different. It's a little bit hotter, but that happens to be an estimation. I don't know. I wasn't there at that hot, dense state, so I cannot say exactly what happened. But if we believe that the Higgs takes a non-zero value and it's some form of a field permeating all stuff and things within our realm of persistence, I don't know, that sounds kind of a little like Star Wars to me. But if we believe it has this non-zero potential, might the reason I have that non-zero potential is to help the elementary unit of action do its thing. And I don't know, does that let us have atoms? Does that help us exist? I hear the Higgs helps us exist because if it was off by a little bit, things would get all wonky and everything. I can't confirm that. I'm not a particle physicist. Again, I'm a dude on the internet, just happens to be extremely interested in this stuff. And I keep on seeing more and more things about different citizen scientists or whatever you want to call it. It's, was it Busy Beaver? Was it number 5 or something? It was solved by some amateur mathematician, literally on Discord. I mean, like I had heard some amateurs had done that, and then was even with the Einstein tile. It was a retired gentleman that happened to work for like a printing company. Gentleman working for a printing company, being able to figure out fancy, complicated tiles that will not periodically repeat. I don't know. It's almost like if you happen to have experience in different fields and niches, perhaps you can apply that experience to other places. Now, with the Einstein tiles, to be fair, he did actually work with some other, I think, geometers, mathematicians, and stuff. Why? Because, well, that's collaboration. You guys are working on similar things, and somebody has something that's useful. Maybe it makes sense. Maybe we should do a little work together, maybe write a paper. And ultimately, one of the benefits for science is as we advance in science, we can advance our technology. As we advance our technology, we can better understand science. So it's kind of like one of those just cum si, cum sa, some yin, some yang, something like that. I'm sure that's blasphemy to somebody somewhere. I apologize. But it's along the lines of, can we actually make sense of what's going on? Because that's my thing. And the whole, actually, to be fair, one of the only reasons why I did that was just because if that has a conjectured way to calculate the fine structure constant. Now, you don't have to believe it, but it's at least a potential explanation. Could be completely wrong, but it happens to also have other interesting properties when you use the expression. And again, it's, did he get the original expression? No, it was brought to his attention via somebody on the internet that was also interested in these things. So if anything, if there is something that comes of this, it's actually the power of the internet and people to be able to do amazing things, especially when we work together. That's my personal opinion. What else do we got? The whole reason I even tried any of that at all was because it was the intuition. I had it a little bit in the paper. So the intuition actually comes from actually the fine structure constant itself. Because one of the things that I noticed when we were going through some different things and checking Thad's numbers with the numbers uncoded and everything, you're kind of going through. One of the things that happened to at least catch my attention was, okay, if you take, let's just go, this is the power from alpha. You can just check things really quick. And again, it might not have the most up-to-date measurements, but for at least a first level approximation, it does a pretty dang good job, in my opinion. Line structure constant. So it's going to give us this number here. Okay. So again, the fine structure constant is defined by this whole thing here. What is this? This is all right. Elementary charge squared divided by 4 pi c epsilon naught h bar. I mean, that's like a mouthful and everything. You're like, what is going on? But if we look at this and we notice, it gives us a dimensionless number. So if it gives us a dimensionless number, and in the numerator here, we got elementary charge squared, aka the charge of an electron or proton. One is negative, one is positive, according to our current convention. So basically, if you square it, it's going to give you a positive number. Okay. So if that's charge squared, that must mean this whole dang thing down here is charge squared. Because if we actually take this and we go, okay, so if we do that whole 4 pi speed of light, epsilon naught is the electric constant. It's h bar, the elementary unit of action, gives us this crazy number here. Now, the only reason that I even slightly kind of saw what was going on here is because I recognize this crazy number because it's used in our inversion boundary for basically the inner or the smaller action that helps to balance things out. But basically, you see this over time times current squared. So basically, time current all squared. Okay. But if we take the square root, oh, looky. That appears to be the magnitude of the Planck electric charge. You all know what that means. That we could simplify this to something along those lines. You could just take elementary. Oh my God, I can't even spell. 3. Oh my God, wow, this is so embarrassing. Oh yeah, dot A. Oh, you're making all these claims. You can't even spell elementary. God, yeah, I know school was a long time ago. So let's do it this way: elementary charge over the Planck charge. Okay. And then we can square this whole dang thing. Elementary charge over Planck electric charge. Wait a second, this number looks pretty familiar. Oh, it seems to be this number. Let's copy this number. Take this. Let's subtract this. Oh, look, we get 0, or at least the 12 significant digits. Don't that just beat all? Which is also interesting because the only reason that I noticed that is because we don't square it. We get elementary charge divided by the Planck charge, which gives us this number, which was the number that Professor Feynman was talking about. That whole, basically, it's the amplitude of the fine structure constant, aka, according to the Physics Monastery, this is J1, the first root of the hyperbolic partition equation. So basically, the whole reason I'm showing you all this is just because I noticed that. I'm like, oh, so you take something that's important within physics, and you divided it by a Planck constant of the same dimensionality. That's why I took the Higgs boson, which is something important within physics, and then just divided it by its Planck equivalent dimensionality. I couldn't make sense of the initial thing, but like this, when you square it, that seems to be what we calculate the fine structure constant to be. So I literally just applied the same intuition from this little thing, and then if we just do the words, and again, what do they have? The Higgs boson mass. See if they updated it yet. Okay, so they just still have 125 GeV. So if we just do that divided by the blank mass, and I get like about 10 to the minus 17. Okay, so 10 to the minus 17, again, it's kind of around the magnitude, the relativistic value of 1 joule. I couldn't make it work without doing something that seemed unnatural or trying to modify it too much. So I'm like, I remember Professor Carroll's biggest ideas in the universe. He's like, you get a result, perhaps it doesn't make sense. I'm ad hocing here. He's like, well, in physics, you get a result, you try to parse it, try squaring it, try taking the square root. So I'm like, all right, I just did this, like square the whole dang thing, just like we did for the exact, to get the magnitude of the fine structure constant. And the only reason is just ultimately because I'm not a good physicist, I didn't set it equal to 1. Since I didn't set it equal to 1, and I'm a crazy person who goes down a lot of Wolfram holes, I happen to recognize the first 3 significant digits and the corresponding exponential power that happens to be bar. So 1.05 times 10 to the minus 34 joule seconds. Again, we're conjecturing here. We don't know, but it's just a new CMS measurement. It's pretty close. Or it's at least within 4 mega electron volts. So I don't think that's too shabby. Yes. Okay. So I think that's all we really got on this. Let's actually go to what we have on the board a little bit. Go over a wee bit of that. Let's see where are we at. Okay. Let me get the thingy out of the way. Might be a little bit hard to see. Let's see what we got over here. Now we got. There we go. Oh, I can turn the thing. Okay, there we go. All right. All right. So basically, that is probably about halfway done. His new book right now, and this book is a much clearer story. It's going to be a little bit of a combination between Einstein's intuition and 44. 44 is basically Thad's best understanding about the current model at the time. And to be fair, it's so much clearer. The arguments now are actually laid out. So I'm pretty sure what we're going to do is once he finishes, we're going to take probably like chapter 3 or something and basically just modify it a little bit more, tidy it up, and be able to actually submit to some different journals and everything. So we spent yesterday going over the book. So different things that we were focusing on. The binomial theorem. So basically, if the whole fact that if we can actually use calculus to actually calculate things and the binomial theorem is useful, that's ultimately kind of how we're constructing things. Making the assumption that perhaps for the first 7 significant digits, things seem to work really well. Because I believe it was Lord Kelvin that said, physics as we know it is more or less done. It's only a matter of measuring the 6 significant decimal place. Okay. Had it stopped at 6, it probably would have been okay. But right about the 7th significant digit, things start to get a little wonky and everything there. So unfortunately, Lord Kelvin was incorrect in that respect. Other things Lord Kelvin had suggested may actually down the line actually come to pass. Totally not vortices in some medium space-time, super fluid, but no ether. It's no ether. Even though Professor Turok, who was on Kurt Mungles the other day, shout out to Kurt and Professor Turok, basically said, well, perhaps you could think of it as almost an ether or something. Oh no, Professor Turok, you used the word. It's a 5-letter word. I don't even know what the. Okay, so where are we else? Basically, we're just trying to peel back and assume that perhaps we could utilize some modular form about piecing things together. Okay, I found it interesting because, oh God, Kurt's been working like a madman. He actually has his new iceberg on Dr. Eric Weinstein's geometric unity. And that was one of the things I initially wanted to help Dr. Weinstein perhaps try to figure out something about geometric unity, not that I'm qualified or anything like that. And I remember I was with Jennifer Sharp. Shout out to Jen Sharp from the Church of Entropy YouTube channel. Basically, we were starting to go through it, and then she mentioned, she's like, well, you're supposed to email Dr. Weinstein if you actually want to work on it. So I sent him an email. I never got a reply. I know, horribly sad. Some random dude. But long story short, probably about 5 days later, Dad had put out his source code 7 video, which just by sheer chance, I happened to be out for a run and open up the dumpster fire of Twitter and like, oh, look, hey, Dad, that's this dude posted a video, just listening to all night on a run and just like, all right, so I'm platonic solid. He's talking about all these different things. I'm like, all right, if half the stuff this guy is claiming is true, it sounds pretty revolutionary, but I take it with a grain of salt because it's a dude on the internet. I'm just a dude on the internet. And then the next day on April 7th, 2021, they released the muon G2 results. And the only reason I asked about it is because it was literally less than a day ago, fresh in my head, as they're talking about, this is our Mars rover moment. I'm like, oh, I guess this is a big deal. To be fair, I didn't know what a muon G2 was. I still don't really know what a muon G2 is. Something it's building up some magnetic potential and it needs to realign and everything, given that how it's going around the accelerator, something like that. Okay. So since Dad's video was fresh in my mind, I'm at work. I'm like, all right, just send a quick tweet. I'm like, I don't know if you covered this the other day, but does this help your model? He responds, yes. So then you go home after work and I attempt to do journalism. What did I do? I go onto Fermilab's website, check on the numbers, not knowing what they were, look at the numbers, go back to that video they had put up the day before about his prediction for the muon G2 results. And I looked at the numbers, look at the error bars. So basically, if you have a 2 in the last digit, it would be either plus or minus that unless they specify otherwise. But long story short, I'm like, dude, man's within the error bars. He predicted the muon G2 results. What's going on here? How did he do that? So I interviewed him a couple of times, and you mentioned if I was on the road, come down to the Physics Monastery. So I did that a couple of times. Bada boom, bada bing, yada yada. Somehow a physics monk. Okay. So that's where we're at right now. But the benefit of the model is we got plenty of predictions. We just need some more experiments. And that was why when CMS, I saw that they had a new publication. I'm like, all right. They were at, it was within about 30 mega electron volts before, but now this new one, it's literally, I'm like, oh, we're within 4 mega electron volts. Now, again, it's still about 2 sigma away, at least according to the value of the Planck mass, but I'm like, all right, it was a bit further below. Now it's a little bit above, and if you're going to look at data, you want to see where you're trending, and you're assuming that we're getting better measurements. And so, hey, we have a prediction right now. We'll see. And again, we're going to need to add more data because and to be fair, is it really a prediction if we've already measured that? Because we have also already had measurements that have, if you look at the data, like around 125.37 and 125.38. So these numbers have already kind of been hit, but now it's going up, down, up, down, up, down, as we continue to hone in. So realistically, we still need about another 2 decimal places to really see what might actually be going on. So we're going to need better precision measurements to be able to see if maybe there is some more there. Now, again, right now, we're within about 4 mega electron volts. Again, could just be a coincidence, but it's something that's increasing confidence. But we're going to need to have folks like from the Atlas collaboration, so the other CERN experiment that does also measure the mass of the Higgs boson, as well as I think Atlas. I know CMS does also measure its width as well. But it's exciting stuff, and I know Thad is going to be finishing up the book soon, and it's going to be a much clearer argument, because one of the things before is 40 foot. Like, all right, number one, he wasn't as clear on it, and you're seeing all these things. You're like, oh my God, what does this even mean? But as we go through, it's like, listen, here are the problems that a lot of folks are running into. Here's the potential reason for why we are running into the problem. Now, might it all come down to some little kink in current because we believe Ampere's constant is precisely 10 to the minus 7? It could be. It could be. If it wasn't 1 times 10 to the minus 7. I know I'm throwing numbers out there, but it was something like, I don't know, like 0.99999, there's one more 91999 times 10 to the negative 8. That's really dang close to 10 to the minus 7, but not quite. That may help explain what's going on. So it also happens to be what we're utilizing as the inversion boundary. So as we're constructing our modular forms for the different constants of nature, it's like, all right, you have kind of like your big standard piece that's going to agree up to a lot of digits, but some may say correction term. This is more of a balancing term, is probably the better way to say it, is that we're trying to balance it, trying to get a closed form, and a lot of it seems to have really good agreement with the data. And even if it's not correct, we at least have a method that we've identified patterns for. And that's one of the big things, because one of the big complaints is, the constants of nature, we can't make sense of them. And if you tell yourself you can't do something, but you're not going to do it. So if nobody believes you can, then why would it ever happen? And that's the only reason I've been able to do any of this, is just because I saw what that did. And I'm like, well, he seems to be doing what other people say are possible. So if he's done the impossible, that must mean that what many folks say is impossible is possible. So that's why some random schmuck like me can just go on there, not be a good physicist, not set H bar equal to 1, and just play around and be like, oh, I recognize a couple of those numbers in corresponding magnitude. What would happen if this would be it? You'd have like 125.376 GeV. You want to know what? I was so terrified. I didn't even include the 6 in my initial version of the paper because I wanted to have it be closer to the 125.35 GeV measurement there. Now I will wholeheartedly include the 6 with the error and everything in there, just because, well, duh, it bolsters my argument. I'm very biased on that. So let's see what else we got. I see you, Jax. Welcome, my friend. Oh, Rick, good to see you. Good to see you. Where are we? Yes, we thank you, sir. We made it back after my car breaking down once more and a couple of plane fights, and yes, standard monastery travel, don't you know? But where are we at? Let's see. Is there anything else to say here? Other stuff we're working on. Let's see. Oh, and then this was a little. Okay. I realize I said you don't always need to. Sometimes things might be missing from natural units. Okay. Now, again, if you really want natural units, I got some stuff with natural units here. And this guy is basically, okay, I'll just touch on this because there's literally, no. I'm not even going to do it. We got less than a minute left. I'm not going to come in and say, oh, good, look at this way. You can look at lambda, the cosmological constant of vacuum energy density. Listen, I'm pompous enough, at least postulating that at the Physics Monastery, we may have figured out some very interesting things. Had some very eclectic people here, but also some really smart folks that have helped out to help better parse what's going on. Because ultimately, that's the goal of science, is it not? Is to get closer to truth. We want to, I believe a wise man said, is cast away our misconceptions something along the lines, basically, be less wrong. So we've hit the hour mark and dinner is ready. So with all that, take care of yourselves, everyone. It's a crazy world out there, but peace out and